If you've ever studied machine learning, you've heard of the bias-variance trade-off. When we're designing a model, the mean squared error between our model's predictions and the outcomes we observe can be decomposed into three sources of error. Two that come from limitations in the model learning process, and one that represents noise that exists regardless of our learned model. The bias-variance trade-off refers to the fact that when we change our model in an attempt to reduce one of these two sources of error, we'll often reach a point where the other starts increasing. But why does that happen? Well, to answer that, we first need to understand what the bias and variance terms actually represent. To make things precise, let's first write y as f of x plus mean zero noise. Here, f of x is the expected output for any given x, which you can think of as the true relationship we're trying to learn. With this setup, for any given x star, the bias is the difference between the average prediction of models trained on different datasets and f of x star. The variance term, on the other hand, measures how much these predictions change as we vary the training dataset. You can think of it like this. If we apply the exact same learning procedure to different training datasets, we'll generally end up with different models. And for any given input x star, each of these models will produce a prediction. The bias describes where the average of these predictions falls relative to f of x star, while the variance describes how spread out these predictions are. So, for example, a learning procedure whose average prediction is close to f of x star would have a bias close to 0, and a learning procedure whose average prediction is consistently shifted away from f of x star would have a bias far from 0. On the other hand, a learning procedure whose predictions vary substantially would have high variance, and a learning procedure whose predictions stay close together would have low variance. So why does the bias-variance trade-off happen in practice? Well, a lot of it comes down to model flexibility. Flexible models can fit the details of the training dataset very closely. This means that across different training datasets, their average prediction can be close to the true function, leading to a smaller magnitude of bias. But because they adapt so closely to the details of each training dataset, changing the training dataset can lead to large changes in the learned model and its predictions, leading to higher variance. Less flexible models, on the other hand, are more constrained, so they tend to focus on broader patterns that are more stable across datasets. This makes their predictions less variable, but at the same time, they might not have enough flexibility to capture more complex patterns, leading to a larger magnitude of bias. So increasing flexibility tends to reduce bias but increase variance, while decreasing flexibility tends to do the opposite. This is why we often observe a bias-variance trade-off during model selection. Keep in mind, though, that this is an empirical pattern, not a universal rule. Sometimes we can improve a model and reduce both bias and variance at the same time.